Hi everybody, welcome to another video in the Algebra section 5.1 eigenvectors and eigenvalues. Eigen is a German word means own or characteristic, proper, have different meaning, and we get back to that when we do some example. Right, let's look at this example. Let the matrix A be 3, -2, 1 and 0, and these two vectors. Find the image of u and v under multiplication by v. How does A affect u and how does A affect v? Right. So it's straightforward. At A times a vector u. Right. Simple enough, we just do it by hand. So that gives us -3, -2, that's -5. And then -1, 0 and 1, so -1. And then let's do A times v. 3, -1, -2, 1, 0 times v, 2 and 1. And that gives us 6 minus 2 is 4. And 2, 0, so that's just 4 and 2. Right. So what's so special about it? Let's just graph both cases. So first we have u is -1 and 1. And A times u is -5, -5 and -1, so that is somewhere around here. Now v is 2 and 1, 2 and 1. And then A times v is 4 and 2. And that is AV. Right. Now first observation, that V and AV on the same line. So that's nice. How about we do something else? Just make up one more. Let W be -2 and -1. So let's see AW. So we have -2, and I'm sorry, -6 plus 2, that's -4, and -2. So now we have W is -2, -1. And multiply by the matrix. That's going to be right. So what we see here is that if a vector align on the v and w direction, when we multiply by it, it will stay on the same direction. That's special. U and did not have that properties. So for some certain vectors, when we multiply a matrix into it, it will remain in the same direction. And not only that, if we pay attention here, we just multiply by 2. So it's not just the vector on that direction, it's always multiplied by 2. So that's why the interesting part here. And that's what we're going to define to be something very special. An eigenvector of an n by n matrix is a non-zero vector x such that a times x is equal to lambda times x. This is the Greek letter lambda. For some scalar lambda, because a scalar lambda is called eigenvalues of A if there is a non-trivial solution x of ax equal to lambda x. Such x is called an eigenvector corresponding to eigenvalues lambda. So go back to the eigen. I mentioned that earlier it is a German word, but of course I don't know German, but I look it up. It means own or characteristic, or before it is adopted, the word eigen in English language is called the proper value. And the concept of eigenvalues, eigenvector was earlier than that, but when it is officially called eigenvector and eigenvalues, it is in the early 1900s, so just over 100 years ago. And what it does, the meaning own or characteristic, is that it is a characteristic of a matrix, I think. And the own is doesn't mean it means like its own values, to something that belongs to a matrix. Right. Now, so in this example, 2 and 1 is an eigenvector and the number 2 is the eigenvalues. Right. Now let's look at this example. Let A be that matrix and U and V are U and V are the eigenvectors of A. Well, we just need to test them. We should be able to see rather clearly. So that is A and U, 6 times -5. So that's 6 minus 30 minus 24. And 30 minus 10, that's 20. Right? And A times V uh, 3 minus 12 and 15 minus 4. Right. So in here we see that if we multiply by -4 and multiply by -4, that will work. Yeah. And here 3 times -9, and this is not. So here there's a number that multiply the vector, that scale the vector into that when we multiply by the matrix. So in this case, U is an eigenvalues. I mean U is an eigenvector. Of A, and V is not. Right. So simple enough. And eigenvalues here is -4. Right? So simple enough. Next, show that lambda equal to 7 is an eigenvalues of A and find the corresponding eigenvectors. Right. So once again, the definition of the eigenvalues and eigenvector is in this a times a vector. It's just the same as the number times the vector. It has a lot of application later. So once again, let's just write down the equation. Right, so we're just going to start with that. We have the matrix A, we have lambda, we just don't have x in this case, which we'll solve for later. Alright. So A is x is equal to lambda x. A is 1652 times x equal to 7 lambda times x. Right. Let's just write this in the vector form. I mean, this is in the matrix form, but let's just rewrite x as x1 and x2. And x1 and x2 here. I multiply it out. Anyway, we have to change this to the linear system. We have x1 plus 6x2 equal to 7x1 and 5x1 plus 2x2 equal to 7x2. Right. Then we have the romantic matrix. I'm sorry, we don't have it yet, because since we have the variable on the left hand side, on the right hand side, just move to the left to subtract 7x1 on the other side. So we should have negative 6x1 and 6x2 equal to 0, and 5x1 minus 5x2 equal to 0. Of course, those equations we know we can simplify already, but let's on that for a moment. Next, we write the romantic matrix. Just need to go back and then to see if I will use x or v, that's all. So this is a homogeneous equation reduced to echelon form. We should have 1, negative 1, 0, 0. I mean, it is easy to see. Yeah, because I just subtract the two equations, they exactly the same. Right. And now we can rewrite. We have x1 minus x2 equal to 0, and x2 is free. 0 x1, x2. Right. And then, of course, from here we can say that x1 is equal to x2. So we write the solution x equal to x1, x2, and x1 is equal to x2, so we say x2 and x2. x2 and x2. And then we can factor out the x2. Or should we have infinitely many solutions here? However, we can choose the simple values of x2. Usually I choose some number that give us we choose some number to give us the whole number, but it is at the lowest term. So let's just say choose x2 to be 1, for example. In that case, we have eigenvector is equal to 1 and 1. Just make things simple. So we have x equal to 1 and 1 is an eigenvector corresponding to if we want all the eigenvectors, then we say all the eigenvector will be in this form. But if we want one eigenvector, then we say that is an eigenvector corresponding to eigenvalues of 7. So that's simple enough. Right. Of course, how do we find the number 7? That will be in the next section. Right. Eigenspace. If lambda is an eigenvalues of an n by n matrix, if and only if those are two sides. A equal to lambda times I, a minus lambda I times x equal to 0. And that has a non-trivial solution. Something like this is a non-trivial solution. And the set of all solution is the null space of the matrix A minus lambda I. And the set is a subspace of Rn is called eigenspace of corresponding to lambda. One thing I forgot to mention, which is rather important, is by the definition, an eigenvector is a non-zero vector, because that is very simple to see that if we have A times 0 is equal to, of course it works for every 0, if for every values of lambda, if it is 0, then that always works. So it's nothing special here if we have a 0 vector. So let eigenvalues eigenvector not be a non-zero vector. Right. Now eigenvalues, lambda is eigenvalues even only if that equation equal to 0. 0 vector has non-trivial solution. The set of all solution here is the null space of A minus lambda I. The set of subspace of Rn and is called eigenspace of A corresponding to lambda. Right. So let's first start with the definition. The definition is Ax equal to lambda x. Well, so that's good. Of course, we can move to one side. And we have a 0 vector, which is good. Now we can factor out the x. If we write like this, that will be a problem, because A is the matrix and lambda is a number. Right? We cannot subtract a matrix to a number. So to make it work, we can just, when factor out, we put the identity here. So the identity matrix I here will have the same size as A, so we can subtract them. So we can always insert identity matrix there. And so from this equation turn into that equation. Right. So that is where we try to find the eigenspace. We're just going to solve for that. Now let A be that matrix, and eigenvalues of A is 2. Find a matrix for the corresponding eigenvalues for the corresponding eigenspace. So now we do node 2, and to find the eigenspace, we want to solve that equation. So we start with the definition, and then we move on one side and subtract. And this is a 0 vector. Sorry. Right. And we just form that, and then we subtract. A subtract I times lambda or lambda times I, it doesn't matter. but usually I say lambda times I. So scalar multiplication that look better. Right. So I'm just going to have the matrix A minus lambda, which is 2, eigenvalues is 2, and then times identity later on we will see that when we subtract lambda times I, pretty much the 2 multiplied to the diagonal. The 2 just multiply to the diagonal entry. 2 multiplied to 0 is 0. So basically this is what we have for, we just subtract the diagonal. Subtract 2, -1, 6, 2, 1, subtract 2, and 6, 2, -1, 8, subtract 2, multiplied by x equal to 0 vector. Right. So we have the matrix 2, -1, 6, 2, -1, 6, and 2, -1, 6. Right. All three of them are equal, so I just subtract the first one to the other two. That will be 0, 0. So the RIF is easy to do here. And the 0 vector, of course, I can just write so I can reduce the echelon form for that. Right. So A minus lambda I, it's just A subtract lambda on the diagonal. And after this we can easily say 2x1 minus x2 plus 6x3 equal to 0. And in here we see that x2 is 3 and so is x3. Yeah, there's only the pivot here. Right. From here we can say that x1 is equal to x2 plus 6x3 divided by 2, the whole thing divided by 2. So from here we can say x1 equal to 1/2 x2 move that, and then plus 3, subtract 3x3 and x2 is 3 or 3. Right. So from here we can say x equal to x1, x2, x3 we have 1/2 x1 that's 1/2 x2, and then minus 3 x3. Of course, earlier we may write like that, and then we split. We have the 1/2 split into two vector. We have 1/2 x2 and 0 plus negative 3 x3 0 and x3. Right, here we can factor out x2 1/2 1 and 0, and then we have x3 negative 3 0 and 1. So in that case we find the eigenspace is in this form, which is the linear combination of these two vectors, right? So we have two vectors multiplied by two constant, two coefficient. So we say the eigenspace is equal to the span of these two vectors. So eigenspace usually when we run out of space and we cannot write a column, we just write a row, but then we transpose it. Yeah, that's because it's not that. It's equal to the span of those two vectors. Right. Of course, the way we solve for that is very simple. We already did that from previous section. The only thing different here, we subtract the eigenvalues on the diagonal, and then we still solve the homogeneous equation the same way. In this case, we have two eigenvectors corresponding to one eigenvalues, and the eigenspace is the span of those two vectors. Right. So we still haven't learned how to find the eigenvalues and eigenvector yet, but that will be in the next section. But now we just have getting closer and closer to it. Right. The eigenvalues of a triangular matrix are the entry of its main diagonal. So in this case, this is upper triangular matrix. See that? This is the diagonal. Everything above it is equal to 0. Sorry. Everything below is equal to 0. Therefore, it's called upper triangular. Similarly, here we have the diagonal here. Everything above it is 0. So this is called the lower triangular. So this is upper triangular. And lower triangular. And if it is triangular, then the eigenvalues will be the diagonal. So eigenvalues 3, 0, and 2. And here for this lower triangular, the eigenvalues will be 4, 1, and 4. So we just say 1 and 4 with multiplicity of 2. Right. More example. If V1, V2, Vr are eigenvectors that correspond to a distinct eigenvalues of lambda 1, lambda 2, and lambda r of an n by n matrix, then the set of the vectors are linearly independent. Right. Next, just find the eigenvalues of A. I mean, the testing is find the eigenvalues of A. So in that case, what do we have? Remember, in this section we only have one thing. A times an eigenvector is equal to the eigenvalues times a vector. Either that, or we can move to one side, and we have A minus lambda I times x equal to 0 vector. Yeah, that's the only thing we have. One of those form. Right now, it's find the eigenvalues of A. So in that case, we just test with the left hand side. That's simple enough. So we just That's a times x. 6, negative 3, 1, 3, 0, 5, 2, 2, 6 times the vector x. Don't know that. Equal to lambda times x. Right, so we work from that equation. Equal to lambda times x. Lambda is 5. Right. So we just pretty much check that the equation from the definition, and now we multiply it out. So a times x equal to 5 times x, right? 6x 1 minus 3x1 3x2 plus x3 equal to 5x1 3x1 plus 5x3 equal to 5x2 and 2x1 plus 2x2 6x2 equal to 5x3. Upon subtract the 5x1 5x2 5x3, on the other side we have 6x 5. Subtract the 5x1, we have x1 minus 3x2 plus x3 equal to 0. 3x1 subtract 5x2 and 5x3 equal to 0. 2x1 2x2 subtract x5, we have plus x3 equal to 0. Right. So we have the geometric matrix of 1, negative 3, 1, 3, negative 5, and 5, 2, 2, and 1. Geometric matrix. Right. Of course, we don't have to do all of that. Remember, from the original matrix, we just need to subtract the eigenvalues on the diagonal. If we do that, we have 1, negative 5, and 1 on the diagonal. Right? Just subtract the diagonal by the eigenvalue. Right. Now let's do the reduced row echelon form. We only need 3 by 3 because the last column is 0, but it doesn't matter. Right, what do we see here? we have 3 pivots, no free variable. In this case, we only have one solution. So we say x1 equal to 0, x2 equal to 0, and x3 equal to 0. So what do we see here? So x equal to 0, right? A 0 vector. Now let's go back to definition. Right. An eigenvector of an n by n matrix is a non-zero. Too bad. An eigenvector cannot be 0. So in this case we say it cannot be an eigenvector. Therefore 5 is not an eigenvalue. Yeah, we can just want to say that. And also, if we look at the previous definition, we say that when we have this equation and it only has non-trivial solutions, we have to have a non-trivial solution, because the 0, 0, 0 solution, the 0 vector solution doesn't count, right? So this is consistent. In the first definition, we have non-zero vector because 0 vectors always work for any lambda. So 0 vector cannot be an eigenvector. And then if we solve that, it has to be non-trivial solution once again, because 0 cannot be an eigenvector. So here we have x equal to 0 is the only trivial solution. So we say there's no eigenvector, so it is not eigenvalue. So there's no eigenvalues. There's no eigenvalues because the 0 vector is not eigenvalues. There's no eigenvector. Actually, there may be eigenvector, but it's just not that 0. So the conclusion here is that since 0 cannot be an eigenvector, 5 is not an eigenvalue. So that is the proper conclusion, because they may be an eigenvector, but it's not. It is something else corresponding to different values. Yeah. Of course, I could go back from the definition and emphasize that from the beginning, but I just wanted to go through this so it show that even though if we have a 0, the trivial solution will not count as an eigenvector. Right. Next, find the basis for the eigenspace of A corresponding to values of 3. Now after this example, it is also note that we just need to write in this form. That will be a lot similar. We almost skip the first step here. So we can just say A minus lambda I times the vector equal to 0 vector. Yeah, in the homework or later you might see that sometimes we write V as the vector, as an eigenvector, but sometimes we write X. Not really matter at all. Just a variable, some vector there. Right. So just going to go with this A minus lambda I, and we did mention before A minus lambda I is just the matrix A it's just the matrix A, but we subtract lambda on the diagonal, and here eigenvalues of 3. You just subtract 3 on the diagonal. Times x equal to 0. Of course 0, you can write 0 or the 0 vector, it doesn't matter. And with that we have the geometric matrix. Just matrix A, subtract lambda on the diagonal. Of course those two are equivalent. So this is 1, 0, negative 1, 3, negative 3, and 3, 2, negative 2, and 2. Yeah, those two equations look similar. I just put in the geometric matrix and reduce to echelon form. I just need 3 by 3. The right hand side is still 0 regardless of the row operation. Right, so that's what we have. 1, 0, negative 1, 0, so 1, negative 2, 0, and 0, 0, 0. Right. Here we have the pivot here and here, and x3 3. So we write the equation x1 minus x3 equal to 0, x2 minus 2x3 equal to 0, and x3 are free variable. Right, then we move everything on one side, so we can say x is equal to the vector x1, x2, x3. x1 is equal to move the x3 on the other side, and 2x3 to the other side, and then x3 is free. So x2 equal to x3, and then factor out x3. So this is an eigenspace corresponding to an eigenvalues of 3. If we want an eigenvector, we just pick one. For example, choose x3 to be 1, and we do have an eigenvector here. In this case, as for the eigenspace, so we say the eigenspace equals span of that vector. So in this section, we define eigenvalues, eigenvectors, and the relation between them with the matrix is either that form or that form. Of course, we use this more often than the other. Give us more direct solution. But in this section, we did not learn how to solve for eigenvalues and eigenvector. That will be in the next section. But we see everybody in that section. Thank you for watching.